All right. Well, very good. I think we're right around 1 o'clock here, so maybe we can get started. For those of you that don't know me, my name's Bennett Howard. I'm technical sales for Sodick on our injection molding machinery line. We've also got Len Hampton, our national sales manager here. Len's kind of sponsored this whole Sodick and Friends webinar series. So as a lot of you probably know, this is I think we're not number 30 here, so it seems like an important benchmark for some reason. But it's been really good. We're pleased to see kind of the attendance that we've gotten, the good feedback, a lot of the good questions. I encourage you guys to continue to ask those questions. I'll explain that here in a second, but. Anyhow, we're happy to have Craig Crossley here from Fortify to talk about 3D printed tooling here with us today. This is something that has come up quite a bit with our customers, and we thought it'd be good to explore a little bit. So I'm personally excited to learn about this as well. So Craig, our presenter here at the top of your screen, will take over in a second. He's the applications engineer for Fortify on the tooling side. He's a UMass Lowell graduate with a plastics engineer, which I think we've had a few of them on, which is always a good way to start. I think what a nice program, and I feel like a lot of the molders on here probably have a UMass connection in some way. So thanks for joining us, Craig, and we're excited to hear what you have today. Real quick, if for those of you that are attendees, we're going to have you do your question and answer. If you can type in, we're going to let Craig go through his presentation. If you could type in your questions in the bottom corner towards the host, which will be myself, and I'll kind of field those questions and pass them on to Craig at the end, and we can get through those. But with that, I think I'll hand it over to you, Craig. Thanks for joining us today.
Thanks, Craig, so much for joining us. Topic of advancements in 3D printed tooling is going to be, obviously, it's well attended here, and we appreciate your time getting together with us and partnering with the Sodick and Friends webinar series. So, so with that said, all the best.
Yeah, thank you guys. I'm really excited for this. This is something that we've been working towards for the past few months, so I'm really excited to see it through. And let's get started. So this is a little bit of a background about me. This is the same bio that many of you would have saw in our press release, but I have about 5 years of plastics industry experience, 3 of those being in sort of an internship and part-time capacity at various different plastics forming manufacturers. So I've worked in resin distribution, resin manufacturing, extrusion, recycling, and injection molding. So I have a pretty diverse background when it comes to different plastics forming. And this is really my first foray into 3D printing. Been at Fortify for about 10 months. And through that time, my major goal has been to introduce high performance thermoplastics into our molding capabilities. Prior to joining, the highest requirement material that we had been able to mold was polycarbonate. So that's around 550 to 575 Fahrenheit, which is great for 3D printed tooling, but my job was really to be to expand that and make us the premier tooling for prototyping. So here's a little background about Fortify. Back in 2016, it was spun out of Northeastern University, which is a school here in Boston. It's a really well-regarded engineering school. We have 5 founders. 2 of them were studying PhDs in material science, and 3 were actually doing a capstone project building a 3D printer. Randall Erb, who is now our director of materials, was an advisor to both of these groups and actually brought them together to create Fortify. They ended up winning Mass Challenge, which is like a startup kind of challenge thing, similar to a lot of other different ones like it. They ended up winning that and using that money to sort of spin out and create Fortify. Not quite what it is today, but what it was to start. That start actually was in the basement of a pizza place. And that was up until about 2020, midway through 2020, they were in the basement of a pizza place working on the first iteration of 3D printers and these materials. When I joined in 2021, we had already moved into this new facility in Charlestown, Massachusetts, which is part of Boston, at the old Hood Milk Factory, which is really cool. It's a brand new facility. They're scaling up now, so there's going to be a lot more places joining in, but it's a really awesome place to be. So if you're ever in the Boston area, you know, just take down my information at the end. We love to have people come in and visit, see the whole operation. You get to see our applications depth, our manufacturing of printers, and our materials manufacturing. So we think that's an awesome way to really get to see everything. So please let me know if you'd like to come visit. Okay, so to get started, not everyone is super familiar with 3D printing, as we know, like myself. This is my first real experience with 3D printing. We are what is a DLP system. So we use a projector to actually cure photopolymers onto a build plate seen here. This is very similar to what we do. There's also SLA, which if you're familiar with like Formlabs, that's the printing technology they use, which is a laser instead of a big projector. There are some real pros to this. The way we do it, you can print, you know, large parts or fairly large parts. You can print really complex geometries without really any barrier to entry. So you're not paying thousands of dollars for any, you know, fixturing or tooling to be able to create these parts, and you don't really have to worry about DFM quite as much as you would with traditional manufacturing. So you still have to design for 3D printing, but those are really the only design constraints that you have to put in. Unfortunately, this also means that there's a real limited materials performance because you're constrained to photopolymers. So what this means is that there are not a ton of great options for end-use parts. It's a lot of prototyping, it's a lot of materials that are subpar, and that can't really be used for any engineering purposes. Another real downside is the production repeatability and quality control. So with a projector curing our resins, you're limited to how close the projector can get to your tolerances. What we guarantee off the build plate is about plus or minus 5 thou, which is 75 micron, which is the pixel size. Now there's some things that we can do to make sure that we stay within that plus or minus 5, but it can't really get much better than that until projector technology gets better. So we are constrained by that, but that's something that happens anytime you have technology that's, you know, driven by other technology. So I will move on from limited materials performance. So I want to hit on that one more time as we move into polymer composites. So these are really high-end polymers. A lot of times they're used in CNC machining to create your end-use parts, but you order them from tube stock, sheet stock, so you end up with a ton of wasted material as well as really long lead times. So I actually worked at a composites manufacturer previous to working at Fortify. Half of our business was molding, half of our business was machining these composites. So I know that they are expensive, they're very difficult to machine, so you need skilled machinists and specialized equipment. Plus, you end up with really long lead times, and like I mentioned, a bunch of wasted material. However, they are a good alternative to metals. They have a lot of different functions like RF devices, chemical and abrasion resistance, as well as you can use them for thermal and electrical insulators. So there's a lot of really great uses for these, but the barrier to entry is really high. Because if you need just one part, it's going to end up being really expensive because of all the specialized tooling that's needed, and it's going to take you a long time to get because you have to go through somebody with a CNC, probably fleet of CNC machines, as well as skilled CNC machinists. So if you're faced with a problem and you need a polymer composite or anything like that, a high-end engineering resin, in order to make your prototype or make your end-use part, but you only need a couple, and you can't really spend the money to get tooling, you know, where are you able to find a solution for that? And that's really where we see ourselves as sort of the bridge between additive manufacturing, design flexibility, low barrier to entry, no tooling costs, and still engineering grade resins that are functional end-use parts. Or in our case, for tooling resin, it's functional prototyping molds for various forming processes, including injection molding, blow molding, thermoforming, as well as some other fixturing. But this is really where we're carving out a niche here, is in this space where we can have high-end materials as well as high-end additive manufacturing. There's really two ways. Well, there's a bunch of ways where we are able to do this, but there's two main ways that allow us to create these really complex polymer composites and print them really well. And I'll go into those. So the first one being, and the most important, is continuous kinetic mixing. So this is, our printers all come with an onboard mixer that's used, seen here. That is where our resin goes in, and that means that throughout the print, we are constantly mixing, heating, and recirculating that material through. The most important thing to note here is that our fibers don't thin out, meaning that you get as close to a homogeneous mixture with particles evenly distributed throughout your print. A lot of you who are familiar with additive manufacturing know that in these type of resin-based printers, you often have a relatively short pot life, anywhere from 8 to 20 hours. With ours, there is no pot life. Since we're continuously mixing it and we don't have any fiber sediment, you're able to print really large parts, or large to our build platform, without fear that the middle of your part is going to look significantly different than the end of your part, which is going to look significantly different than the beginning of your part. You're going to end up with a nice evenly distributed fiber mixture and a nice end use part that is hopefully what we consider fully isotropic. So that brings me to our next, which is the FLUXPRINT system. This is our magnet system that aligns our fibers to the axis that we like. So for mold tooling, we align in the Z-axis. This, along with the CKM, hopefully will create as close to a fully isotropic part as we are able to. This obviously being so that you can print a part to the best of its ability, not necessarily aligning a part to the best of the material's performance. We want you to be able to align those parts on the build tray however you want or however they fit best. For example, if you have a mold that you want to print, maybe it has an insert or a couple inserts, in the way that some places would, or some other molds would have you print, you need a certain way in order to get the material characteristics that you want for better performance. Our goal is to make sure that you can fit both those halves on the same build plate with all your inserts and make sure that you're getting the best time investment. And so we'll move on here. One thing to note before I move on actually is there are 3 different Fortify printers. There's the Flux Core system, which is used for RF and ceramics. There's the Flux One, which allows for Z alignment for the magnetics. That's used for our tooling resin. And then there's the Flux 3D. That allows for tooling alignment in all 3, X, Y, and Z. And you can switch the magnetization per layer. So you're able to really align those fibers per layer, which is generally used for materials development and new end-use parts that would be very complicated. I don't work a lot with any of the Flux 3Ds, but they're really cool, and I would definitely suggest getting to see one in action. Okay, so those 2 things, CKM plus the FLUXPRINT, have allowed Fortify to develop this digital tooling resin, which is a highly filled ceramic reinforced photopolymer. So it's an acrylate base that was developed by Henkel. So it's a proprietary base resin that they send to us. We mix in our ceramic fiber packet in order to increase the strength, rigidity, and most importantly, I think for molding is the HDT. As you guys can see here on our data sheet, we're at an HDT of somewhere over 300C. That 300C mark is right around 570, I think it's 572 Fahrenheit, which is about what we run polycarbonate at in the barrel. So the heat that the mold is actually seeing is probably a little bit less than that because we open our gates up pretty significantly to reduce shear heating. So while that mold is probably never going to get up to 300C, that's really the lowest benchmark that we needed to hit in order to get that increased performance. So we're seeing performance in temperatures above 700 degrees Fahrenheit. We just haven't tested the HDT test that high yet. So we know it lies somewhere above 300C, but we're not quite sure where. And I'm not sure that there's going to be any testing going into that, as we haven't seen really any need for it. So along with that high strength, rigidity, and HDT, enabling that higher performance than traditional polymer tooling, another key factor for digital tooling is that it can be polished up to an A2 finish. We are not professional polishers, so we have done this, and that A2 is sort of like an anecdotal A2 finish. Our customers have said, yeah, this looks close enough to an A2 finish. But we do have customers that will be onboarding soon the ability to professionally polish with real polishing tools and people who are actually skilled in polishing. So we think that we're going to be able to hit A2, possibly better, but at the very least, when necessary, you'll be able to hit those like really glossy finishes that you'll need for some parts. And that's actually really unique to our material. Not a lot of polymer tooling can be polished, and not a lot ends up polishing to where you're getting parts that look like they were made off an aluminum tool, which is something that's really exciting. We don't do it often because it's time consuming, and a lot of time in prototyping that's not super necessary, but it's really cool for those companies that are contract manufacturers that are selling parts. If they get an order for 50 parts, but they need to be really high quality, you can still use digital tooling to do it. So you're getting those parts that look great and you're getting them really fast. All right, so I want to go through a few different case studies just to show you guys, a couple different uses of polymer tooling as well as, specific to Fortify tooling. This first one showcases our ability to lightweight mold tools. A lot of people, traditional manufacturers, get a little skeptical when you talk about lightweighting just because they've been burned in the past a lot. And I can totally understand that. I'm the same way. My background is all in traditional manufacturing, so I understand the skepticism when a lot of this stuff comes to 3D printing. But this test really showed that lightweighting our tools made no impact on the performance. We were able to reduce print time, reduce material cost, and run the exact same process with nearly the same results. This is, however, a great time to introduce the Fortify molding process. We're able to use really low clamp tonnages because of our material's ability to compress together. So we generally print slightly proud of our mud frame there, so that we can really squeeze those blocks together and get a nice parting line seal. So we're only using 5 tons of clamp tonnage for this. We're using a 2,000 PSI injection pressure, and we are running a pressure limited process, meaning that once we hit that 2,000 PSI, we're willing to give up control of the speed. So for our press, which is a 30-ton Nisei with a 19mm barrel, we give up control of that 10 millimeters per second once we hit that 2,000 PSI. We're not in large-scale production, so having control of those variables doesn't quite matter to us as much as it does to get a nice defect-free part. And we find that for tool life, tool longevity, and part quality, this is the best way to run. If you guys are familiar with Influx, it's a very similar way to the way that their software operates, but we use pressure limited. So we're running at super low pressures compared to what traditional manufacturing would do. Really low speeds, almost like we're extruding the plastic into the mold, which is another reason why we run with really long or really high barrel temperatures and really long cooling times. So as you'll see, an 80-second cooling time is obviously not ideal when you're making more than, let's say, 25 to 50 parts, and that's totally understandable. And we do also add an additional 30 seconds to that cooling time for an air blast. You'll see those hoses there. Those blast the face of the tool for 30 seconds to cool it down back to around room temperature, probably slightly higher, in between shots. And we found that significantly increases the tool life and performance. While we're heating that barrel really hot, we're taking a really long cooling time, one of the first things we get asked is about mechanical properties. One of the ways we combat, material degradation is to put a either charge delay or plasticizing delay, depending on which, press you have. The vernacular can be a little bit different. But what I'll do is run with an extremely low cushion. So something in like the 1/8 of an inch or, a couple millimeters, in order to have as little material in the barrel sitting there heating up. And then I'll put like an 80-second or the full cooling time. So instead of having my plasticizing take up 70 to 80%, like in traditional molding, I'll have it take 0%. I'll take that full 80 seconds, plasticize, and then let it sit in the barrel for 30 seconds, which I think is more common cycle time that you would see in traditional molding. So our material should not see any more heat, plus very little shear heating during the molding process, and our mechanical properties should be about the same. Another thing to go into here is you'll see the 20-second total injection time. So the press we have takes into account injection, like fill time plus pack and hold, all in one time input. So if you have like a 1 to 5 second fill time, which is really common for us, and then a 10 to 15 second pack time, which is another really common thing, that allows us to get rid of any voids, sinks, any other defects. It really allows those air bubbles to escape through either ejector pin holes or designed in venting. But that 20 seconds is also like really common cycle time for us. So we're looking at 2 to 3 minute cycles for a lot of parts that we do. So we generally recommend to keep the quantities under 250 parts. We have done more, but that's really for time savings. 250 parts is usually where we like to keep it. So here's some of the results from this. This is a 50-shot mold test. So we only run to 50 shots. We don't run to failure. So we didn't see any failures with this mold on the original or on the lattice mold. What we did see, however, is a significant reduction in resin and in time. So for an 8.5-hour print, you're likely not starting that as soon as you start your day. So if you're not running a 2-shift or 3-shift factory, you're looking at an extra day of print time. Whereas with a 6.5-hour print, you're saving 2 hours. You should be able to get that in before you leave for the day, and you're starting your bake cycle a whole day earlier. So our normal cycle would be start a print Monday night, let it run overnight, come in Tuesday, clean, post-process, let it bake overnight on Tuesday, come in Wednesday, and you're ready to mold. With this, if you started early enough, you're cleaning and post-processing before you leave on Monday, putting in the bake cycle Monday night, coming in on Tuesday, ready to mold on Tuesday, which can be really significant, especially for contract manufacturers or anybody that are selling parts as a service. Or if you're an OEM who needs to do a bunch of iterations, shortening that by a full day can be really, really beneficial. Another really beneficial thing is the money savings, obviously. So you're reducing your material by 29%, meaning that, after 3 molds, you're already saving an additional mold. I find this to be the most interesting for a contract manufacturer who's, maybe taking an order for 500 parts or something, and you expect the mold to last for 150 or so parts, and so you need to know that you're printing 3 copies. So even if you get more, and you quote at the fully solid mold tool, you either are baking in an extra 30% profit for yourself, or having a buffer for an extra mold to be printed in case you're not hitting that number. So this can be a really useful tool in a lot of cases. We don't do this super often, but it is something that we'll employ if we think that it'll be really helpful for us. And I think that this is a really useful tool that was done in conjunction with Entopology, who did all of the design for these latticing. And it worked really well for us, and we would be really excited to see people using this in the future. So this second case study is actually the most fun project I've worked on since I've been at Fortify. This is a glass-filled ULTEM cutting bit. 2 key features on this part would be that cutting edge. It's a little tough to see because this part is black, and then those threads there at the bottom. So they're exposed threads that we decided to just put right on the parting line. One of the most interesting things about this part was that the customer asked us to make it as quickly as possible. So they didn't really care about the DFM. All they wanted was to have parts in hand as soon as we could get them. So in order to do that, instead of taking the extra few hours, maybe even a full day, to design in a series of slides or pulls in order to make that undercutting cutting edge, we decided to just go with a sacrificial insert. It's a few cents of material, and you just crack it open with a hammer once you're done. That took our design time from a day, maybe 2 days, down to a few hours. Less than a few hours, actually. It's probably an hour and a half. It takes about 10 minutes to design that insert, and then maybe an hour to put in all the ejector locations and a few other things. But those threads worked with the mating piece perfectly, and we ended up getting a really nice part out of glass-filled ULTEM. Some key processing features. This is the highest temperature we've subjected our molds to, at about 760 in the barrel. The mold probably saw somewhere in that 700, 750 degrees. And the highest pressure, or second highest pressure actually, that we've shown our molds, the highest being 15,000 psi with a different ULTEM part. But this was really the first time that we had ever tried something more high requirement than polycarbonate, and it went perfectly. They needed 50 pieces, so we ran 60 with a 10-piece buffer. The only sort of wear or anything that we saw was a little bit at the gate, and that was easily trimmable. So all it did was really open up the gate and allow for a little bit lower pressure to be used, but it worked great. The other thing is we really broke all of our rules. So our high injection pressure breaks our 10,000 psi limit, which we usually set for ourselves, and then the low fill time. So I was running at machine maximum speeds here in order to get this to flow. As you know, if any of you guys have molded with ULTEM before or anything else really high temperature, you're running with a mold that's 350 to 400 degrees Fahrenheit. Our molds are run at room temperature, so we didn't do any preheating or anything. So in order to get this to not freeze off, I had to be running as fast as it could go. So our fill time was around 0.3 seconds. It is a lot different than our normal 1 to 10 seconds that we usually run. But it worked really well, and I think that this perfectly showcases our ability to run high performance materials as well as really or closer to manufacturing processes. So higher injection pressure, higher fill speed, higher temperatures. We can do that. Obviously, it's not the best for our tool life, but it does show off that capability. So what I wanted to do here is, using this as an example, go into some time savings and cost savings that you see using polymer tooling in general, but more specifically ours. Okay, so here's a quick Gantt chart I threw together. They got quoted about 8 to 12 weeks for their aluminum mold. I thought this was kind of a long time, but that's what their quote was for. So I decided to put on this chart the best foot forward from this particular tool supplier. I gave them 2 days of mold design time. That's obviously not making any sacrificial inserts with aluminum, so you have to design in those slides. And then only a day of contact before the PO was agreed on, and then mold manufacturing starting that day. And then they said 8 weeks was the shortest, so I gave them the benefit of the doubt and put 8 weeks on Monday that you'd send out the tool. This is something that's fairly common. A lot of times you'll see those lead times get down to 4 to 6 weeks, but much faster than 4 weeks is not likely unless you have mold making capabilities in-house, which, as I'm sure many of you know, is becoming less and less common as it's harder and harder to find skilled CNC machinists, and you generally don't want to waste them on prototype tools. So sending these out to other people is generally what happens, and tying up skilled labor is not ideal. So if we move down to this bottom section here, you'll see sort of what happens with our process. Like I laid out before, you do your mold design on Monday. You can start your mold printing on Monday after afternoon or night, depending on what time you're leaving. It prints overnight. You come in on Tuesday morning, you take it off the printer, you clean it, you do a quick UV cure, and then once it's ready to go in the oven, you put it in an oven bake. It goes through about an 8-hour cycle, so we do that overnight. We come in the morning, we do a permanent mold release coating, and then we're ready to mold 4 hours later. So usually by Wednesday, early afternoon to mid-afternoon, we're getting our first shots off. So this one, we were able to ship parts Wednesday afternoon. Right before I went home, I shipped out those parts. And so they ended up getting their production build started, 8 weeks earlier, which can be huge for companies that need either new product development to be faster or beat competitors to market, which is where we see a lot of people heading, is that, the cost savings is great, but the time savings is almost more important. But if we move on to the cost savings, you'll see that they're pretty awesome. They were quoted at 30 to 40,000 for a steel tool, which I thought was a little bit high, but that's what the quote came in at. And they quickly realized that they were not going to be using steel for this, so they went with a lower requirement aluminum. which came into about $10,000 to $12,000. So this chart here shows that, obviously you're paying your first third or so, 30 to 40% upon agreement. You're getting your next after you get your first shots, and then you'll pay the full amount once you get the mold. So after, that 8-week to 12-week range, you'll be out $12,000, but you'll have your mold. Compared to a normal 3D printing service. So if you just decided that you needed some prototypes, you don't necessarily need your end use material. You can just print some parts. That's going to be a pretty linear curve. So every time you order parts, probably going to be the same cost every single time. And you just order parts as you need them. So whether that's new iterations or you only need it at once, it's going to start pretty low, probably under $1,000 or right around $1,000. Now, our printed tool costs about $500 to make, and it was done in the 3 days that you guys saw earlier. So that's that little blue dot there. It's really hard to see because it's a lot quicker and a lot cheaper. However, if you do need multiple iterations, if you didn't like the way it first came out, you can do a second iteration that same week. So you could make your design changes Wednesday, start the print, and be ready to mold again on Friday. So you're looking at 2 prints for about $1,000 worth of material in the same week. So for the same cost, you could be doing 10 different iterations, as different as you really want them to be too. So I think that's really, really valuable, almost invaluable, to be able to do design iterations with your end use material, as well as for other examples, you do a lot of DFM work, which I think can be really, really important, especially early on in your process. So you're getting your production tool build done 2 months in advance, getting you to market and starting to make money 2 months in advance. All right, this last one is probably the most, it's probably the coolest one. It was an end cap for a baseball bat for Dee Marini and Wilson Sports. So those of you who played, in Little League or maybe in college, you've probably used a Dee Marini bat before. These are the end caps that go on the end. We actually did a not two shot, but an overmold. So we molded this piece right here, seen on the first, and then we molded the end cap around it. So some of the key features here are those automated slides you see on the second image. They used a compressed air ejection, obviously overmolding, as well as molding 2 separate pieces for that overmold. A textured surface, you'll see in that first picture, and tool polishing. So some of the faces on that first picture were actually polished in order to create like a textured finish on the end part that you'll see on the next slide. And then harder to see on this is actually a raised parting line. This is something that we really like to do to keep our clamp tonnages down. It allows you to exert force on just the area where you want it. So you can use, that 5 clamp tonnage like we showed in the first part, or maybe even less, instead of, setting it to the machine maximum and just letting it run. Like I've seen at a lot of the places I've worked, those presses ran, if we had a 30-ton press, it ran at 28 tons, and you never really, it's just a set it and forget it type variable. So the material on this one is proprietary. We were told it was similar to like a PCABS blend. I'm not positive on what that means. I assume it means it was PCABS, but it could be something different. But I'll show you guys the finished part here. So as you guys can see, that is just from tool polishing, those 2 different textures on that first picture. The reason that they decided to try this out with us is because they wanted to test different materials, different colors, and then different foils. So there's actually a foil that creates that color on the lettering there. It's not colored plastic. So they wanted to try all those different things out, but they didn't want to pay for a different tool every time. So a great thing for us is that we can print several different tools. So if you have different shrink rates, it's not going to be prohibitively expensive to print a new insert just for that plastic, whereas it would be if you're going to have 10 different ones machined out of aluminum. Plus, a 12-hour print for all components means that you're ready to go exactly in that 3-day timeline. So instead of, let's say optimistically 3 weeks to get a mold set for this, we're looking at 3 days. You can do multiple iterations, multiple materials, allowing them to fail faster. We do actually have a published case study for this one. So if you wanted to go through and learn a little bit more about it, there's definitely that available. And that's really what Glenn from Dee Marini wanted. He wanted to be able to fail fast. So they want to know what doesn't work just as much as they want to know what works. And that's really something that we can facilitate, being able to show you guys, what tool designs work, what tool designs don't work. And polymer tooling in general is great for that. But if you need something that's, more than higher requirement than just a polypropylene or a TPE or something like that, you need something with a high HDT, high strength, high rigidity. And that's really where we see ourselves coming in. All right, let's move on to some general just guidelines that we like to adhere to. These are all vetted out on different molds that we've run. The first column being a mold that's, on the medium size, in that like 4 inches by 4 inches by 6 inches that we really like to stay in. Those are ones that not a ton of flow obstacles, so we can keep the injection pressures really low. But these are also, the lowest pressures that we've been able to push that material into a mold with. On the flip side, the other column would be the highest pressures. So something that's really fine detailed, something that we had to close the gate on, or just material dependent. Those are really vetted out through all of our experience. So we spend a ton of time validating these internally. The injection speed column is a little bit specific to our machine. So that one we take kind of with a grain of salt. It really helps you if you have the same machine as us, not quite so much otherwise. So that's why we include the fill time. These are just recommended fill times. This is what we find for best, tool life and longevity. Obviously, for something like ULTEM and LCP, we've had to fill really quickly so that we don't freeze off on that room temperature mold. But as you'll see, for a lot of plastics that we're able to get flowing well, we go to that high-end fill time, almost more like an extrusion process than it is like a true injection molding process. And that's just so that we don't deflect core features, so that we can keep our tool running smoothly and get as many parts as we can out of it. So the bright side with being able to run those high performance materials is that we can do it and we can almost always hit the shots that we need to. The downside is it's unlikely we're going to be able to take an ULTEM mold to 10,000 parts like we could with a polypropylene part. And then the last column here you'll see is the cooling time. Now this is generally where people get a little bit freaked out, right? You see cooling times up to 140 seconds and you're going to think like, this is ridiculous. How am I going to produce 10,000 parts with a 2-minute cooling time? Well, that's why we keep our part numbers really low. We really highly recommend that you keep it below 1,000. We have run parts longer than 1,000, and a unique feature of ours is that you can definitely use ejector pins and definitely run in fully automatic. We do that really often. Anytime that we don't need a hand-loaded insert, we're running in full auto, and that's unique. It's our ability to maintain our structural integrity throughout the part during many cycles of clamping, of introducing heat, introducing pressure. Those don't wear out, and it doesn't affect our ability to eject parts off of the tool. So the cooling times are long. A lot of times, though, you can get away with running it full auto, so you don't have to be, running it in semi-auto and have somebody there the whole time. And then if you focus your attention to the bottom here, we have our higher requirement materials. Those have really been my focus for the last 10 months, introducing ULTEM to our envelope. Polyketone, LCP is another big one. I'm sure a lot of you are familiar with Sodick, so you're probably really familiar with LCP. So if you need that, it's really cool. It works really well. We were able to do a micro molding prototype part with LCP, and it worked great for our material. So that was a really exciting project that we worked on. And then PET. The one issue that we've come across with PET is over-crystallization on a preform specifically. So we're not able to actively cool our parts yet. We are working with a mold flow analysis software company to get through conformal cooling to see if we're able to actively cool our molds instead of the passive cooling with that air blast. So we do see that with PET, we spend too much time in that higher temperature range and create overcrystallization. So we're not getting like that nice clear preform that we would have liked. But that is something that we're going to be putting a lot of effort into in order to fully address other applications. But we do have a really deep application knowledge. We have 2 tooling applications engineers. And then obviously in our other applications, we have a lot of knowledge there as well. But if you have any questions about materials processing, we have guides available. And this is obviously best practices for Fortify. But even if you're using another tool, feel free to reach out and I might be able to help. or steer you in a better direction with this stuff. Okay, so if, at this point, it's probably a question that gets asked every time we do one of these, is how would you go about getting parts? We have an evaluation program, or you can order them through a service provider. So if you're looking for quick turn parts, we're able to turn that around, like I said, in about 3 days. Generally, that's gets backlogged a little bit because there's multiple projects going on all at once. But you can definitely take down Dan, who's our sales manager, his information, my information, if you just wanted to talk about the technology or other 3D printed tools. And then Empire Group is the service provider that we work with fairly often, and they have this capability, and they're able to really do some fun stuff with Fortify tooling. So my last slide here, I just wanted to focus on some of the other applications that we provide. I am definitely not an expert in any of these, so if you have any questions about these, please take down my email, send those to me, and I will get you in touch with the right person. I can answer some really high-level stuff, but I'm by no means an expert in this. We do have an RF materials partnership with Rogers Corporation. They've helped us develop the low loss 2.8 DK and the low loss 4.9 DK. I know that they're used a lot of times for lenses, and we're printing a lot of lenses, but other than that, I'm definitely not your guy for any of the RF materials. We developed ceramic materials in partnership with Tethon, who's out in the Midwest. We actually don't do any ceramics printing in-house currently, but they have a Fortify printer, and they're doing a ton of materials development, including making a low shrink aluminum silicate, and then a high purity alumina, which is at 99.8%. That's that second image down there, that white part. Two that we've developed with Henkel, aside from just the digital tooling resin, is a high temperature ESD resin used for like PCB fixtures or maybe even soldering nozzles. Also used, as you can see there, those are surface mount pick and place nozzles. Those could also be used for this ESD resin. It's the same base as our digital tooling, so it's got that high strength, high rigidity, but with ESD properties. And then we also have a TCDR, which is our thermally conductive resin, as seen there. I believe that is a heat sink or a sample of a heat sink. And those are produced in-house at Fortify in partnership with Henkel. And then the last one I wanted to touch on was our flux developer. So one of the things that makes our printer really unique is that it's an open platform. So you're able to print not only the materials that we offer, but materials that we don't offer. So you can take Flux Developer and get access to a lot of the back-end stuff to be able to either develop your own materials, or if there's a material that we don't offer or isn't in the Henkel portfolio, you can just onboard it on there and be able to play with different settings. We see this most often with materials developers, but you could also use it as just, if you have a material that's offered by somebody else that we don't currently offer, you can either ask us to develop one for you, or take on Flux Developer on your own and be able to just print that material with the settings that will work. So with that, I think I would like to move on to some questions. So if you guys have any, please send them in. That is my contact info. Thank you to Sodick, and I'm really excited to answer some questions.
Great, thanks, Craig. That was great. I think really informative. We do have quite a few questions here, which means you did a good job. So I think I'll just jump right in here. If, like Craig said, type your questions in here as they come into your head. But hopefully we'll get to all of them. There are quite a few. If not, like you said, take down Craig's information here, and you guys can connect afterwards. Okay, let's start from the top. So first question is, with these speeds, can you handle injection for micromolding, and can you achieve the tolerances required in micromolding?
Yeah, so the speed question, I'll answer that one first. Yes, we did do some micromolding. I can't remember exactly what the dimensions were, but I think the tightest one was like 1/10 of a millimeter, around there. It's pretty small. We did it with LCP. It worked really well. Unfortunately, our tolerancing is still that plus or minus 5 thou for the mold itself. So obviously with really tiny parts like that, we didn't take measurements, but I imagine that with a lot of micromolding, you're going to have really, really tight tolerancing. So we're really looking in that like prototype phase. Probably hitting close to what you would need, but I definitely wouldn't want to make any guarantees that we can do it.
Okay. This one's a little bit wordier here. See if we can get it right. So it seems to me like this is more of a volume increase alternative to 3D printing rather than a quick turn alternative to steel tooling. Is that a correct statement? I'm interested in a prototype tool, maybe 10,000 to 5,000 or 50,000 shots. Sorry. Hopefully that.
Yeah, so it's definitely not an alternative to steel tooling. It's more of like if you have a situation where you need somewhere between, you know, 1,000 or like 100 to 1,000 parts, so higher volume than 3D printing, as well as getting your DFM done for molding so you can get to your production parts sooner. That 10,000 to 50,000 is really, you're probably better off just cutting aluminum at that point. But I'd say under 5,000 is really where we see ourselves. So you're able to get your end use plastic in your end use process, and really get a lot of that DFM work done early, and get your prototypes that are meaningful. So a lot of times in 3D printing, just direct 3D printing them, those prototypes are great for maybe one or two parts, but they're not great for if you want to do any functional testing or if you need, you know, your end use material. But yeah, if something like it's definitely not an alternative to steel. Steel is going to have tighter tolerances and definitely a higher shot life as well.
Sure. Okay. Next one here. What is the minimum thickness of each layer in your 3D printing process for these molds? Can you print molds that are capable of microprocessing with a homopolymer?
Ooh, I don't know the last part of that question, but I can definitely answer the first part. We print at 50 micron layers, but we can get down to 25 micron. We find that 50 is the best as far as like speed and resolution goes. So we print all of our molds at 50 micron layers. If you want to send in a little bit of a clarification on microprocessing a homopolymer, I am not positive on what you're really asking there.
Okay, well, why I asked that, whoever asked that question, maybe take that offline and reach out to Craig. You guys
Yeah,
can dive
definitely.
into that. Okay, moving on. Okay, good one here. Can you judge prior to molding to see if you will have an issue filling parts because of the pressure limited? Slow, for example, slow velocity, low pressure filling may not be working. Is it predictable? That's a bit of a tough one.
Yeah, actually, we find it to be fairly predictable. A lot of the geometries that we run can sort of be bucketed, by like what they look like. And a lot of times, you know, Ben, who's our other applications engineer, and I have enough experience running different parts to know, you know, where things are going to be tough to fill out, where things might fail. And so we do a lot of like either insert molding, adding extra vents, to really mitigate these. And then we do also have an internal calculator that hopefully in the next couple months, I'll say, will become an external calculator. So you'll be able to put in, you know, different inputs as far as your material that you want and your geometry that you want, and it'll spit out a certain number of shots that you can come to expect. But yeah, it is really predictable. If you have a mold flow software, that'll also, you know, be pretty helpful. But just by looking at it, we have a pretty good idea of what is tough for us and what is really easy for us.
Gotcha. Okay. A couple of these I will take here just logistically. As far as a copy of the presentation, we will be posting this, I know, to our YouTube page. Craig, I don't know how you guys will share it, but we will have a recording of this whole webinar here available after the fact. So I just wanted to get that off the table. Okay, next question. What are the smallest dimensions that will work with this process and polypropylene specifically?
Sure. Smallest dimensions, I'd say that we can print has really come down to pixel size. So 75 micron, just about. That's pretty close. I mean, that's pretty much as little as we can print. But feature sizes on molded parts, apart from just micro molding, are usually bigger than that. So we don't run into a ton of issues on too small. The biggest one we run into is too big parts. Our build platform is 8 inches by 4 inches by 13, or 8.5 by 4 by 13. So the largest axis is obviously 13 inches. And a lot of times people will say, oh, we have parts that are much bigger than that. But much
Sure.
smaller is not something that we generally run into.
Okay. Thanks. Yeah, I think you actually handled the next question there as far as what's the largest, the other end of the envelope.
Yeah,
Um,
so we don't print like standalone tools. We generally use either, depending on what you have, it would be a universal frame or a mud frame, and then we use cam blocks to put those inserts into place. So
mhm.
we can fit, a decent envelope of parts for people, but obviously if you're making something like bumpers, we just wouldn't be a good fit.
All right. What is the best quality surface finish of your tools?
Sure. So as printed, it's going to look like a 3D printed part. So a high resolution DLP part, but it will still look 3D printed. You'll see some, slight evidence of layer lines on those faces. The best polishing that we've done internally, once again, like I am not a skilled polisher. Ben is not a skilled polisher. That's sort of just learned on the fly. We have been able to get up to an A2 finish for a customer. So they took a look at it. They said, yeah, these parts look like the parts that come off of our A2 finished, aluminum molds. We imagine this could get better with professional polishers and equipment. And we will hopefully be learning that in the next few weeks as we have somebody who's very interested in polishing those parts to getting a really nice glossy finish. But yeah, A2 as of right now is the best we've been able to get to.
Right. Okay. Good one here. What design changes would you have to make from your tools to, say, a production tool?
Yeah, so that's an awesome question. That's one we get all the time. With things like core pins, we generally will, if it's really high aspect ratio, we'll replace that with just a metal component off of McMaster. If it can't be replaced, we'll ask for 2 to 3 degrees of draft. If it can't be, that's doable. We can deal with 1 degree. Half degree gets really tough for us just because of the way the roughness on our as printed surface. It'll get a little bit dicey to get it ejecting nicely. But yeah, generally about we ask for 3 degrees. We can go as little as 1 degree, and we replace really high aspect ratio features with either inserts. So whether that's a printed insert to de-risk failure on that, so we can print up a bunch of them, and if one breaks, we just swap in the next one, and it's really easy. Or we use an off-the-shelf just metal component, like for a lot of like bosses and stuff. We'll just throw in an order or a pin from wherever, as long as it's like a standard size, and that works really well for us. So we de-risk a lot of things using inserts and pins, and generally we find that the change to a production tool is minimal, if that. Obviously, on something like the case study I showed earlier on that cutting bit, the change is going to be huge, right? Because we didn't even take the time to design in any slides or anything. But on that part, like the DeMarini one, there's really minimal changes that's going on.
Right. So I'm not sure which tool this is referring to, but someone asked, how much would that tool cost in material alone? I'm not sure. Maybe you can give an example.
Sure. So the first tool was, if you saw, the material alone was about $200. That second tool with the sacrificial insert, I think we printed 2 copies, so it's like $300 for each mold set in material cost. That's pretty common with that type of size. We'll see something in the $300 to $500 range for material costs.
Okay. Uh, we're got about a few minutes here. We'll finish up, but I do have maybe one or two more here. So if you have questions, please get them in now while we've got Craig here with us. Um, okay. Do you ever make 3D printed tools and send those tools to customers, or do you only run in parts with your tools in house?
We generally avoid sending tools to customers. We would much rather have somebody come in and see us run them. It's better to get to see the printer itself. It's better to have us running them because, this is what I do every day. And there's some considerations that you need to take when you're inserting the tool and when you're running the tool. We have, a program set up where you can come in, you get to see everything, get to go through all the training. And that's really the best practice. Obviously, there's some special considerations when somebody either already has 3D printed tooling or a ton of experience. We'll print tools and send them out, but generally we avoid that.
Okay, thanks. Let's see here. What is the highest quantity of parts you can get off of a single tool? I don't know if you covered that or not.
So the highest quantity that we've gotten off to date was like 4,000 in one run, and we only stopped because I just got kind of bored and wanted to stop running it. Like it didn't fail or anything. It was just we were only doing it to see how many parts we could get, and the mold didn't fail. It was a gear part, so fairly simple looking. But yeah, it just kept running. So if you need to make gears, we can make thousands for sure.
Great. Well, that's all the questions I think we have for now. I think hopefully everyone feels like we covered their questions here. Thanks so much, Craig. I thought that was really good. I know I see Len jump back on. Maybe you want to say a few words here, Len.
Yeah, no, that was fantastic. Thanks, Craig, for sharing your technology with us, and we would like to extend our invitation to you can share your machine with us on our brand new showroom floor if if you so inclined. But no, thanks so much.
Thank you
Yeah,
guys
no,
for having me. This was
yeah,
awesome.
that was fantastic. I think everybody got a lot out of it, and certainly, uh, you know, text or email us if you need more information from Craig, and we'll make sure he gets the questions that you might have that maybe weren't talked about today. So, but again, thanks so much. I think that was very informative, and you got a heck of a machine there. So, um, and thanks for everybody that attended.
Yeah, thanks guys. This was
Right.
a lot of fun. We get to do it again sometime.
Yeah, we'll talk to you soon, Craig. For those of you still on, I think our next one coming up in 2 weeks will be with RD Abbott in the silicone space. So you'll see marketing materials, but we are going to keep going here with the Sodick and Friends webinar series. So keep your eyes peeled. Thanks everybody for joining once
Thanks,
again.
everybody. Thank you.
Thanks guys.
Take care, Craig. See ya.